give you a tiny bit of background about Coq, and then give you a very quick kind of run through of the first chapter, the one that I asked everybody to do as homework, and then basically just give you a chance to get started on it right now and run into any install problems or IDE problems or things like that in a context where there are people around to help. So that's the plan for the next 40 minutes or so. So to begin with, why are proof assistants a suitable topic for this summer school? Why are we spending time on this topic? There are a few reasons. Maybe connected, but not necessarily. So one reason is that proof assistants, and Coq in particular, is a really beautiful illustration or embodiment of all of the theory that you've been hearing about so far and that you'll hear about in the coming days. Coq's core is a dependently typed functional programming language. That is to say, a powerful constructive logic. And I think it's really nice to get a chance to get these concepts under your fingers in a way that is difficult to do with just pencil and paper work on exercises. So this is one motivation. The other motivation is that proof assistants are beginning to be very much used in research on programming languages. And the reason is basically that people were beginning, well, starting quite a while ago, starting maybe 20 years ago, but then with increasing urgency, people were beginning to feel that they were overwhelmed by the scale of the problems that they were trying to, of the proofs that they were trying to do. So back in the good old days, 40 or 50 years ago, you could write a nice paper about, we didn't call it programming languages then, but it was, and even up to the first decade or two of Popl, you could write a really nice paper about programming languages by writing down a system of 6 rules and then beating it to death for many pages, and each of the proofs would be interesting and deep and short and easy to check. And those days are not completely gone, but if you look at a typical Popl paper now about some interesting programming language feature, the definition can go on for pages. And the proofs can go on for dozens or sometimes more than 100 pages. And if you think about how confident, would you stake your life or even a lot of money on the absolute correctness of a proof that goes on for 100 pages? No, of course not. That's ridiculous. No one, not even the authors, can check a proof that goes on that long. Possibly one person has checked it carefully, but I think probably not even that. So how are we going to be confident about proofs that are that big? Well, fortunately, proofs that are that big tend to be boring. This is both good and bad. If you're checking them by hand, it's bad. But if you want automated support, it's good because it means that there's some hope. And so what people have been doing is just forced by the facts of scale that the field is dealing with, have been more and more moving into formalizing and mechanizing their results. Mechanization has other benefits. It has many costs, which you'll be finding out. But it has some hidden benefits as well. One huge benefit is malleability. So even if it were possible to carefully check a 100-page proof, as soon as you've changed the definition a little bit, and now the whole 100 pages needs to be checked again, now it's completely impossible. So if the definition itself is big enough to be interesting, it's going to be big enough to be changing. And that means that being able to prove something about it once and then fiddle with the definition a little bit and then see what you need to alter in the proof and so on is an enormous win. Structuring your proofs so that you can do that is a whole topic unto itself, which perhaps we'll talk about a little bit later in the week. But at least you have some hope. There are other benefits. Formalization is sufficiently difficult that even a slight infelicity or suboptimality in your definition makes maybe a factor of 2 or a factor of 10 or a factor of 100 difference in the difficulty of doing the proofs. And if the proofs are taking you many, many, many hours, dozens or hundreds of hours, you're going to put in the work to make the definitions as beautiful as possible, and from the point of view of science, that's good. Okay, so proof assistants are a natural topic for this summer school. There are many different kinds of proof assistants. There are fully automated theorem provers. There are fully manual proof checkers that do nothing but look at a fully detailed proof and check that the rules have been applied correctly in a very local way. And then there are, in the middle, so-called proof assistants that are not fully automatic, but neither are they tediously fully manual. And Coq is one of the prime examples of a system that fits in the middle. Why do we like the middle? Well, it's clear why we don't like the fully manual side. That's way too much work. The reason we don't like the fully automatic side is it's way too hard. People in AI are still working very hard on building actual automatic theorem provers that can prove interesting theorems. Great strides have been made, but we're not there yet. It's extremely hard. So to get work done in the meantime, we have these tools that attempt to mitigate the low-level tedium while still relying on you, the prover, for the key insights. These tend to be power tools. So Coq is not something that you can pick up and be using at an expert level in just a couple of hours. You really have to understand what's going on and spend some time with it. But I think you will find that, well, A, it's fun, and there's the kind of video game effect that people talk about, that proofs are actually, there's a endorphin response when it says, yes, you proved that little lemma, even if you've spent a ridiculous amount of time on it. So there's, sorry, where was that sentence going? It is fun. And I think you will find that the work that you need to put into it to get good at it is amply repaid. It falls in the same category as Emacs and Tech and things like that for people in our area. However, having said that, Coq is not the only good proof assistant out there. It's the one that we happen to have chosen because it's one that I happen to like, and it's one that a lot of people in the PL area are choosing. But there are a couple of others that are worth mentioning. So Isabelle is another very widely used proof assistant. And its main advantage, I would say, from the point of view of the kind of work that we do, well, it has two advantages over Coq. One is that its notion of equality is extensional, and we'll come back to exactly what that means, but the short version is it eliminates a lot of low-level tedium in proofs involving equality. And then a second thing is it has a much better story about variable binding. So if you're doing proofs, if you're formalizing something that involves binding variables, like a programming language, you're in for a certain amount of pain, no matter what. Isabelle has a very nice so-called nominal data type package that enormously lessens that pain. So those are some reasons why you might want to consider Isabelle instead of Coq, although Coq is the one that we're dealing with today. Another one that you might like to look at is a system called Twelf that was originally developed by Frank Fenning. And that I would say the difference between Coq and Twelf, so Twelf is also based on a higher order intuitionistic logic. It is a little bit more explicit and less automated than Coq. However, it's got a much better story again about variable binding. So 12th is a more targeted tool. It doesn't work for everything. Its logic is substantially less powerful than Coq's. But if you are if your application is something that 12th is good at, then it's very well worth checking out because it may well be the very fastest path to your goal. Okay, so enough about generalities. How many people here have successfully installed Coq on their machines? Okay, almost everybody. How many people are still working on successfully installing Coq on their machines? Anybody at all? Cool. All right, one or two. One thing to make sure is the Coq that you'll want for purposes of this week is not the absolutely newest one. It's 8.3, which is the previous release. So 8.4 is the present release. 8.4 is almost compatible with the Software Foundation's stuff, but since 8.4 is not widely used yet, we're still sticking with 8.3 because there are a couple of places where there are incompatibilities, so we have to choose. So you'll want Coq 8.3. How many people have, although they've installed Coq, not done any playing with any of the IDEs or? Okay, good. So let me talk a little bit about the possibilities there. So you can drive Coq straight from a terminal window. You don't want to. So you want some kind of an IDE that's going to help you with moving back and forth in proofs and showing you the state of the proof at each point. And there are two. There's one that comes with the Coq installation called Coq IDE, which is a fairly simple kind of standalone GUI that puts up a window and shows you the text of the proof script that you're working on and has a couple of buttons for pushing commands at the underlying Coq interpreter. The other one that people use is called Proof General. Proof General is a package that runs inside Emacs. So you have to buy into Emacs, but you should do that anyway. Anyone who thinks that's false should use Coq IDE. They're both fine. The Proof General is more sophisticated and does more stuff and is built into Emacs, which you should be using anyway. But Coq IDE is fine for our purposes. So use whichever you prefer. Just use one of them. Okay, so now a tiny bit about the specifics of Coq. So Coq is sort of two things. It is at its core is a functional programming language called Galena, a very rich and expressive functional programming language called Galena with a couple of slightly strange twists from the point of view of mainstream functional programming languages. The main strange twist that you'll notice right off the bat is that in Galena, all functions are total. So it has recursion, but all recursions have to terminate, and it has to be obvious to the Galena type checker that they do. So that can sometimes involve a little bit of unusual locutions in the way that you write things, but usually, by and large, the way you write Galena programs is the way you write ML programs, and even the syntax is similar in some ways. So you can think of Galena as a core subset of ML or a typed lambda calculus with an extremely rich dependent type system based on, well, what we saw this morning in Bob's lecture. So a typed lambda calculus with dependent types, also with polymorphic types in the style of ML and Haskell and all your favorite languages, and also with a built-in inductive definition facility, which I'll show you more of in a second. And for this reason, the core lambda calculus that is at the heart of Galena is called the calculus of inductive constructions. Okay, so I said there were two parts to Coq. One of them is Galena. It's at the center. And then wrapped around Galena is the so-called tactics layer, the tactics language. And the way things work together, and again, we'll come back to this in more detail, but the way these work together is doing proofs in Coq is essentially, as we've been seeing the last couple of days, constructing lambda terms of appropriate type. So a proposition in Coq, in Galena, is a type. A proof of that proposition is a term of that type, an inhabitant of that type. And doing proof in Coq is constructing terms of desired types. Okay, so when you write down a theorem, you're proposing a type, and when you write down a proof, you're demonstrating that that type is inhabited. Now, there are two ways to do that. The low-level way, which kind of ignores this surrounding layer of tactics and just concentrates on Galena, is you can write down your theorem, that's a type, and now you can just write down the term in Galena, and now you're done. Okay, so you've written a term of the appropriate type, and that satisfies your obligation to show that this theorem is provable. Those proof objects, when the theorems are large or interesting, can get big and they can get complicated. So this is, in many ways, not a very nice way to work. You perfectly well can. And it's interesting to do it just to kind of get the feeling of what's really down there. But it isn't the way that people really work. The way people really work is to get some help. So in the following style, which I'll demonstrate in a moment, propose a type and now ask for some help in constructing a proof that is a term of that type. So we begin with the type and a sort of empty term, and now if the type happens to be an implication, well, how do you prove an implication? You assume the left-hand side, and you try to you assume you have a variable of the left-hand side, and you try to prove the right-hand side. That is, find a term, usually using that variable of the type of the right-hand side. And so there's a command called intros that kind of invents some variables and internally constructs a lambda whose body is still to be filled in. And it says, okay, now you need to prove this. So you're kind of, you're interacting. So you have this tactic for what is effectively a programming language, where you are imperatively manipulating the state of a partially constructed lambda term. And when you finish filling in all the parts of the term, then the proof is done, and Coq accepts it, and you go on to the next thing. So the way it works in practice is you propose a theorem, and then you go into a different mode where you're giving tactics, you're applying tactics, which gradually massage the state of the proof until the set of sub-goals, the set of places in the lambda term that aren't finished yet, where you haven't filled something in, becomes empty, and then you're finished. The materials that we'll be using during these 2 weeks are a book called Software Foundations, and this is one chapter of that book. This is a book that a number of colleagues and I have been working on for some years now, that I use at Penn and that's used a number of other places for a one-semester kind of beginning graduate course on the core theory of programming languages and constructive logic and theorem proving with proof assistance and so on. I think given the level of people in this room, we're probably going to cover most of the book in the few lectures that we have. So I'm going to go through it pretty quickly. I think you'll find that the book is written at a sufficiently basic level that going through it at that speed will not be a problem for most of you in this room. In order to get ready for starting in at a good speed on Saturday, let's take a look at this first chapter, and then I'll invite you to start working on it with the aim of finishing all of the exercises in it by the time we start on Saturday. So every chapter in this book, every bit of this book is a Coq script. So you'll see on the screen, usually when I'm lecturing, an HTML presentation, which is automatically generated from the ASCII presentation, which is the real one. Okay, so make sure I'm looking at the right version of this. Okay, so here's the .v file that Coq actually understands, and not there. Why is that not giving me the window that I want? Okay. Okay, there we go. Just get it again. And this is the HTML version. So let's actually look at the text version for the minute. So this is what you see if you're using Coq IDE. And here we have an inductive type definition. So this is the I part of constructive CIC, calculus of inductive constructions. This says to Coq, we're defining a type. So this is going to be, from now on, considered as a built-in type. You can think of it as a data type in your favorite functional language. It has 7 constructors. That is to say, there are 7 primitive expressions that are inhabitants of this type. And if we do Control-C, Control-C is the Coq IDE, is the Proof General version, but in some way, send it to Coq. And Coq's response is, okay, I've defined the type day, and I've also defined some other things that we're going to find useful later. In particular, we've defined an induction principle for reasoning about elements of this type. Okay, so we'll come back to induction principles and all that. Basically, what we're doing so far is just doing a little functional programming. Okay, so just to overview, the contents of this chapter, this basics first chapter of Software Foundations, is some functional programming, which should surprise none of you, and some very simple tactics, just a handful of tactics that you can use for simple proofs, including simple inductive proofs, about simple functional programs. So it'll get your feet wet with both. Okay, so this was how to define a data type. This is how to define a function in Coq. So this is Coq's notation for function definition and then pattern matching. So it takes a day called D. It returns a day. It does its thing by matching D with that list of patterns and returning an appropriate element of the type day in each case. And we can present that to Coq, and it says, OK, I got it. Now, having done that definition, we can do some computing. So we can simplify expressions like next weekday of Friday. So eval simple in is a command to the Coq top level that says, take that expression, the parenthesized one, and simplify it using the simple simplification method. Coq actually provides several ways of simplifying expressions. Basically, what all of them are doing are using reduction rules, like the ones that we've seen from Bob and Frank, to reduce the expression to some simpler form. Okay, so simple is the most used one. There are several others, so you can say eval compute in something, and that applies a different set of rules which basically work harder. So eval simple just does kind of, despite its name, it actually isn't simple to explain exactly what it does, so I don't want to get into details, but it does the beta reduction steps that you would think, plus some unfolding definitions, like next weekday was a thing that we defined, and these different modes of reduction have different behavior, for example, when they come to definitions like next weekday. Okay, so let's not go into detail about that until maybe later. For now, all you need to know is think of eval simple in as an atomic unit, which asks Coq to please find a simple form of this, or please evaluate it to a result. Okay. We can also prove theorems. So this, although it says example, it's actually a theorem. So the keyword example there is a synonym for, actually there are several synonyms that all mean the same thing to Coq. So you can say example, you can say lemma, you can say theorem, proposition, a few others. They all mean the same thing. They're read as follows. The thing that comes next is the name of the theorem or example or whatever that we're introducing. And then what comes after that is a proposition. That is to say, a type. So the equality here is an equality claim. That is, it's an equality proposition. So this second line there is the proposition that is provable if the left and right-hand sides are definitionally the same, that is, the same modulo reduction. So when we submit this command to Coq, it changes modes, as I warned you a few minutes ago it would. So we're now in the mode where we've presented it a theorem, and now it wants a proof. And the way that we're going to give it the proof is by tactics. So here's the proof script. So the word proof is basically just syntactic noise. You can actually leave it out, but people put it in just for readability. So proof is a signal to the reader that we've entered proof mode, and Coq is now waiting for a proof. Sorry. Okay, so Coq is waiting for a proof. We're in a state where there's one sub-goal, namely the main goal. If we ever apply a tactic, let's see, so what would be an example? If we apply the tactic that corresponds to the pair introduction rule, so if we're trying to prove a conjunctive statement, A and B, and we apply the tactic that corresponds to conjunction introduction, that rule in the lambda calculus has two premises, or that rule in the logic, if you want, has two premises, prove A and prove B. So if we apply the tactic corresponding to that rule, we're going to get two proof obligations. Please prove A, and when you're finished, please prove B. So at any given moment, there will be some number of sub-goals, all of which have to be eventually discharged in order to be finished doing the proof. At the moment, there's just one, and for this very simple proof, there's only ever going to be just one. So next tactic, so here's your first tactic. It's called simple. So there's a potential for confusion here. We've seen the keyword simple twice. They're not exactly the same. They invoke the same reduction procedure, but one of them was a top-level command asking Coq to just reduce an expression and show us the result. This one is a tactic that says, please take the goal and reduce it as much as possible, or reduce it using the simplification method. And the result is a new goal, Tuesday equals Tuesday. Why? Well, because the simplified result of next weekday of Saturday is Tuesday. Okay, so that tactic resulted in this simplification. And now one more tactic is so-called reflexivity. Reflexivity is a tactic that is particular to equality proofs. So the reflexivity tactic is only applicable when the goal is an equality statement. And it proves the statement, generating no subgoals, if the left and right-hand sides are indeed the same. Okay, so now the response from Coq is no more subgoals, the proof is done. And the last thing we do is issue the QED command, which takes us from proving mode back to the top level. And the response from Coq is test next weekday defined. Remember that test next weekday was the name that we gave to this theorem. So effectively what's happening is Coq is building up a context in the technical sense, a gamma, is building up a context with bindings for all of the theorems that we've succeeded in proving. So the top level gamma of the Coq top level at this point in the script now contains a variable test next weekday of type next weekday of Saturday equals Tuesday. Okay, any questions up until this point? Okay, please ask questions as we go along. All right. So, yes, please.
Is there any way to and print it and just see the steps?
There is. Afraid of what's going to happen when we do that, but let's try it. Oh, it's not so bad. Okay, so the proof is eRefl Tuesday. Why is that the proof? Because of the way equality is defined internally in Coq, which we'll come to. We'll talk about that in detail. But just to preview, Coq's internal logic, the Galena language at its core, is extremely simple. It hardly has anything built in. Basically, what's built in is implication. So it's extremely simple. Not even equality is built in. In fact, not even the usual logical connectives, and, or, not, and so on, are built in. All of those things can be defined. The definition of equality involves a constructor called eqrefl, and we'll come back to the details. Okay, so this is showing us this eqrefl of Tuesday is the proof object in the calculus of inductive constructions that has that type. Okay, so maybe speeding up a little bit now. The Booleans are not built in. We can define them. That's a little more usual. So Booleans are an inductive data type with two constructors, true and false. We can define functions like and, or, not. The only thing interesting about these is just showing you the concrete syntax for multi-argument functions. Internally, of course, all multi-argument functions are curried, but you get the convenient concrete syntax. And let's see. Okay, so next thing to show you is here. So this is an exercise. Right. This is an exercise, and it's preceded by a tiny bit of magic. So the magic is the word admitted there. admitted is a command that you can give Coq while you're in proof mode that says, I don't feel like finishing this proof, just trust me. So, and we're using it in a slightly magical way here. You don't need to understand the details of that line that defines admit at the moment. What's important is that is the type of admit. Admit is a value of type t for any t. Okay, so admit is a completely magical value which we can use to fill in for a term of any type whatsoever. Naturally, if we ever tried to compute with such a thing, we would have a problem. But we're using it here basically just as a placeholder for something that you're going to fill in when you do the exercise, and for purposes of just having a script that we can execute later bits of when the exercise isn't done, we'll fill in the body of this function with admit. So your job when you do this exercise, it's a very easy exercise, is to delete the word admit and replace it by an actual term of the appropriate type. Okay. What else? This is obvious. Coq includes first-class functions, just like all functional languages, and just like the lambda calculi that we've been playing with so far. So nothing really to talk about there. And then continuing on kind of quickly, because I want to give you. Thank you. Check. Okay, so I showed you print. Print takes something from the environment and prints its value and its type. Check prints just the type. Okay, now going on quickly. We are not going to have time for very much. Actually, let me ask you. I can talk through some of the rest of this file for a few more minutes. Or we can stop at this point and give you a chance to get your fingers dirty trying a few things yourselves. Which would you prefer? So let me take a quick vote. I'll ask for both options this time. So how many people would like to just hear a few more minutes of me gabbling on about what's in this file? How many people would prefer to stop and just play with exercises? All right, about 50-50. So I'm going to choose to continue talking for a minute and then stop. So that's just like compromising on 9:30. Let me kind of skip forward, just kind of telling you what's on each screenful. So we defined the Booleans and some functions over them. Here we define the natural numbers and some functions over them. And the main thing that this is showing is pattern matching, which is basically just like pattern matching in your favorite functional programming language. So not too much interesting there. One thing to note is that when we do recursion over natural numbers, we use, or over any, whenever we define recursive functions, we use the keyword fixed point instead of the keyword definition. And Coq will check that this fixed point is terminating because the n prime that's being passed as the argument to even b is structurally a subphrase of the original input n. Okay. We can define infix notations using some notation definition facilities. Nothing too interesting there. Okay, now we come to more interesting theorems. So the theorem here is nothing very different than the example we had before, the examples we've had up until this point. Just the type that is being claimed to be inhabited is a bit more interesting. It's got a for all in it. And then the equality proposition under the for all has some variables. But even so, because of the way plus is defined, it's recursive on its left argument, this theorem can be proved just by simplification. And I'll let you see that for yourselves as you're playing with this. Okay, so some theorems we can prove, some interesting theorems, slightly interesting theorems, we can prove just using the facilities that we've seen so far. Others need a little bit more. So here is a little bit more interesting theorem. So this theorem is a hypothetical theorem, and it says n plus n equals m plus m. So that's not true just by simplification. It is true by rewriting, that is, replacing equals for equals. And the way we do it is, so here's the proof. So the first thing we do is we use the intros tactic. I skipped over the explanation of it. Intros moves some variables from the goal to above the line, which is the assumptions that we're using to try to prove the goal. Okay, so now the goal is prove this under those assumptions. Those assumptions are not too interesting. More interesting is the assumption that n equals m. And we've given it a name, h. And now on the next line, we're going to use h to rewrite the variable, let's see, we're using it left to right. That's what that arrow means. You can also use it right to left. We're using it to replace the left-hand side of h by the right-hand side. So we're going to change the n's to m's in the conclusion. And now we can finish by reflexivity. Okay, so this is proof by rewriting, and this is the fundamental way of using equality propositions, equality hypotheses. All right. Sometimes, often, usually, the thing that we want to prove about a number depends on which number it is. So there, we're going to need a way of saying, well, is it 0 or is it successor of something? And the way we do that is with this tactic called destruct. So here's a simple thing to try to prove. So BEQ-nat is a Boolean function that tests whether two numbers are the same, returning a Boolean. And we'd like to prove that when n is a number, n plus 1 is never equal to 0. How can we prove that? Well, we can't prove it directly because we can't simplify the last line because n is a variable. But we can prove it by case analysis on n. So if n is 0, then we can simplify. If n is non-zero, then we can't completely simplify, but we can simplify enough to know that BEQ-nat is definitely going to return false. Okay, so the simple reducer is able to deal with expressions with variables in them as long as the variables are kind of buried deep in the term. It can reduce the expression around them. So that's what's happening here. So now we have two subgoals, and each one of them is solved by reflexivity. Okay, here is a little bit of magic that you skip over. But the way that you use the magic that we just skipped over is when you're doing proofs by cases or proofs by induction, it's convenient to name the cases. It's convenient to be able to write, this is the case where B is true, this is the case where B is false, if we're case analyzing a Boolean. And so this case tactic with a capital C is just a little bit of, well, it's a little bit of programming in Coq's tactic programming language, which we'll come back to in a few lectures. So you don't need to understand the details of how it works, but it's a little program in Coq's internal language that defines this case tactic. And you'll see that, that as we're, I'll just show you now, as we're working through the proof, you'll see that the proof state includes this string b equals true that helps stay oriented in which case of the proof we're working on. And when we finish the case and move on to the other subgoal, that string disappears, and now we can add another string using this, using the case tactic again. Okay, so last thing, and then we'll go or hang around and do some experimenting, is induction. So simple case analysis of numbers is enough to prove some things, like the little theorem we looked at a minute ago, but to prove interesting things about numbers, you need induction. To prove almost anything interesting about numbers, you need induction. So here's how it works. So you have something in the hypotheses in the environment of type nat. Type nat is an inductively defined type. We introduced it using this inductive keyword. And remember, at the moment when we did that, an induction principle was defined. The induction tactic uses that induction principle to generate appropriate subgoals corresponding to the cases of a standard inductive proof. So we say induction n, and then this as thing is just doing a little bit of helping with naming. All right, so 30-second digression. Many of the tactics in Coq involve introducing variables. If we just say, for example, induction n, it will automatically choose variable names in the subgoals as it likes. Here, what it's going to do is choose the name n for the number in the subgoal. But that's a weird thing for it to do. I find that a confusing way to think about the proof, because the n in the subgoal is actually the predecessor of the n that we originally started out with, because in that subgoal we're dealing with the case where the original n has the form successor of something. So what Coq has done is, since we're not using the original n anymore, it's just reusing the name for the thing that the original n is the successor of. So that's just bizarre. So I recommend always using this as annotation on the induction tactic, which allows you to control its choice of variable names. Okay, so the vertical bar is saying there are going to be two subgoals. I don't care about the first one because it's the zero case, and there isn't any variable binding. The second case, I want you to use n prime, not n, as the name of the variable. Okay, so now let's look at what happens. So when we do the induction, we get two subgoals. The first subgoal is to prove the theorem that we're interested in the case where n is 0. And that proof is easy by reflexivity. And then the second one is to prove the thing that we're interested in where n prime is some number, and we get an induction hypothesis that says n prime plus 0 is equal to n prime. All right, so this is a standard inductive proof, Coq style. Okay. And that is all I wanted to tell you about this file. So, so those of you that want to, let's stay around for a few minutes, and why don't you take a chance to do a few exercises. So at the beginning of the file, you'll find some simple functional programming exercises. go ahead and do them. They'll take you 5 minutes, and they'll get the syntax, the concrete syntax under your fingers. And then there are some more interesting exercises. In particular, there are several, I think maybe 3 recommended exercises. The first 2 are easy. The last one is a little bit more challenging, and chewing on it will give you a little bit deeper experience with thinking about how to do things the Coq way. So I recommend doing at least all of those recommended exercises and as many as you have time for in the next few days of the other exercises in the file. You'll also find, so what I was showing you just now was the terse version of the file that I like to lecture from. There's a bunch more text that explains all of this in quite a bit more detail in the version of the file that you should look at. Final note, the version of the file that you should look at is the one that is now, as of 1 hour ago, linked from my homepage. So if you go to my homepage and follow the link to Software Foundations, you'll find a brand new version that I just exported this afternoon of the lecture materials, which I may re-export slightly newer versions over the course of the week, but they'll be different only in small ways. So that's the up-to-date version. Okay, have fun. Any questions, first of all?
Like a short, something like what the keyword means, something is there a shortcut to pull up
like theorem or something like that? Plenty of text in the chapter. You'll be fully explained.
Okay, and the dots, they are like sequencing points that they separate.
The periods at the end of commands, they're the Coq, that was the end of a command.
Two couple questions. Number one, is there any kind of a cheat sheet on the Coq's ID itself?
There must be a cheat sheet on the Coq ID.
Number two, is there any written instruction for someone who does not know Emacs for configuring Emacs and Proof General? Yeah.
And there are many people in the room that can help you with that, and that love to have new Emacs users.
About file versions, on the webpage it has date 17th of July 2012, but the files that are downloaded have the date as April 2nd, 2012.
Yeah, that's fine. So the front page of the book says 17th of July. But the files themselves have older dates. That's because those files individually haven't been changed for a little while. So that's fine. Any other questions? Okay, have fun.